So this is the last part of SHM. So this is the last video. So in another video, so we'll start the new chapter. See children, here some physical systems performing SHM. So what are the some physical systems performing SHM? Suppose you have a log of wood. So you know that log of wood will be floating in the liquid or in water. So some volume of the log of wood will be outside the liquid and some volume will be inside. So here force of buoyancy balances mg. Now if we slightly depress the log of wood downward and release it, it will jump up and down and it will oscillate up and down. These oscillations will become SHM. What is the time period of that SHM? This is the time period. So when you slightly depress it downward, so extra volume of the solid will get submerged, extra volume of the liquid will be displaced, and so there will be extra force of buoyancy in the upward direction. So because of this, so there will be an upward force, and because of that upward force it will jump up and again jump down because of gravity. It keeps on oscillating. So the time period of this is 2 pi so root over m by a rho g. Here m is the mass of the log of wood and a is the cross-sectional area of the log of the wood and rho is the density and g is the acceleration due to gravity. Here rho is the density of liquid, children. Rho is density of the liquid. So remember that. Because here we need to substitute force of buoyancy. Force of buoyancy is volume of the solid submerged into density of the liquid into g. Then, so other physical systems. So next, you will see the time period of oscillations of a piston. Suppose there is a gas, ideal gas taken in a cylindrical container and a piston is fitted so with this cylindrical container. Now this piston is in equilibrium. The mass of the piston is m. A is the cross-sectional area of the tank or container, and what is the time period of the piston? So the piston will make oscillations if you slightly push it leftward and release it. If we slowly push it leftward, then isothermal changes will occur. If we push it suddenly, then adiabatic changes will occur. If we push it slowly leftward and release it, then the piston will oscillate, so like this left and right. And what is the time period of those oscillations? This is the time period of those oscillations for slow displacement. So if we displace the piston slowly, then this is the formula. So m is the mass of the piston, h is so the height of the gas inside the container, p is the pressure inside, and a is the cross-sectional area. Now suppose if you push it suddenly, then adiabatic changes will occur. Then the time period will be 2 pi root over m h divided by gamma pa. Gamma will come instead of p, so gamma p will come in the denominator. So remember, children. Then after that, so time period of oscillations of a liquid. Suppose you have taken a liquid in a U-shaped tube and slightly depress the liquid in the left limb, then the liquid level will rise in the right limb. So this is some extra liquid beyond its level in the left limb. This extra liquid will have some extra weight. This extra weight will cause the entire liquid to oscillate. The time period of the oscillations of this liquid will be 2 pi root over h by g. H is the height of the liquid in one of the limbs. So after that, you will see physical pendulum. What are physical pendulum? Any rigid body can be suspended so from the rigid support, and if you slightly pull that rigid body and leave to itself, then it will perform oscillations. What is the time period of these oscillations? So 2 pi root over I by mgd. I is moment of inertia of the rigid body about that axis of rotation. Moment of inertia. Then m is the mass of the body, rigid body. mass of the rigid body, and g is acceleration due to gravity. D is the distance between point of suspension, distance between point of suspension, point of suspension and center of gravity of the body, and center of gravity of the rigid body. So many problems can be asked so based on this. So how, suppose I have a rod, okay, so a rod of length L and mass M. So now if I slightly displace it and release it, it will execute SHM. What is the time period of that SHM? So T is equal to 2 pi root over I. Moment of inertia of this rod about this axis is ml square by 3. ml square by 3. And so Gm is the mass, G is acceleration due to gravity, and D is the separation between point of suspension and center of gravity. It is L by 2. So it's just simplify, you will get the answer. So next you will see torsional pendulum. What is torsional pendulum? A disc so is connected to a string or wire like this. Now, if you slightly rotate the disk and release it, it will so execute SHM like this. It will perform angular SHM. The time period of this angular SHM is 2 pi root over I by k. I is moment of inertia of the disk about that axis. Moment of inertia, and k is called torsional constant. K is called torsional constant. So the torsional constant is for the wire from which the disk is suspended. After that, energy in SHM. So, potential energy in SHM is given by half m omega square x square. Kinetic energy is given by half m omega square into a square minus x square, and total energy is half m omega square a square. So remember children, the total energy remains same. That is PE plus KE remains same in the SHM. The total energy in SHM remains same. So PE plus KE remains same. PE will vary, KE will vary, but total energy, that is PE plus KE, remains same. So PE will be varying, KE will be varying, but the total energy remains same. Questions will be asked like this based on this formula. Find the x value where PE equal to KE. Find the x value where PE is 1/3 of the total energy. 1/3 of the total energy. So like this, questions will be asked on this concept. Okay, then we go to the last part, that is damped oscillations. In damped oscillation, these two formulae are very, very important, children. So how amplitude decreases? Amplitude in the damped oscillation decreases exponentially. There will be one damping force, so like frictional force. Because of the damping force or frictional force, so the amplitude decreases exponentially and even energy also decreases exponentially. How the amplitude decreases exponentially? This is the equation. So here A naught is the initial amplitude and B is called damping constant here. B is the damping constant. So B is damping constant. The damping constant depends on the damping force, the frictional force or viscous force. Then m is the mass of the particle executing SHM. And this is how energy varies. So E is equal to half m omega square a square. In place of a, if we substitute that half m omega square a naught square e to the power of minus, so the whole square of that will be minus, so 2bt divided by 2m, the 2 will be cancelled and you will get this expression. So these two formulae are important, children, in damped oscillations. So that's all, children. So in about SHM, then in the next video I'll start a new chapter. Thank you, children.